Hi everyone, welcome to another interesting session on the topic haloalkanes and haloarenes. In our previous class, we have learned the first two chemical properties of haloalkanes. The third chemical property of the haloalkanes is the reaction with metals. Now, haloalkanes react with different metals to give different products depending on the nature of the metal. For example, if they react with active metals like lithium or aluminum or zinc, they give rise to organometallic compounds. Organometallic compounds are those compounds in which metal atoms are directly linked to carbon atoms. However, if they react with magnesium metal, they give rise to a special type of organometallic compounds which are called as Grignard reagents. And if they react with sodium metal, then they give rise to alkanes. Let us see some examples of these reactions. If we take a haloalkane C2H5Cl chloroethane and we react this with an active metal like lithium, these reactions with metals take place in the presence of dry ether. So in the presence of dry ether, lithium metal will react with the haloalkane, that is chloroethane here, to give an organometallic compound C2H5Li, which is named as ethyl lithium. Similarly, if we have another active metal like zinc, then two molecules of this chloroethane will react with the zinc metal in the presence of dry ether to give another organometallic compound, that is C2H5,2Zn. This is diethyl zinc. So whenever these haloalkanes react with active metals like lithium or zinc, they will give rise to organometallic compounds like this. In the second case, if these haloalkanes react with magnesium metal, then we get a special type of these organometallic compounds which are called as alkyl magnesium halides or Grignard reagents. So here, if chloroethane reacts with magnesium, then we get ethyl magnesium chloride. Note that here in these compounds that were formed, the metal is linked to a carbon of the alkyl group. But in this Grignard reagents, a halogen atom as well as an alkyl group is linked to the metal atom. Now, the third case is where these haloalkanes react with sodium metal. Now, in the presence of sodium metal in dry ether, haloalkanes, they undergo a special type of reaction which is called as Wurtz reaction. And in this reaction, an alkane is formed as the main product. So here, if we have two molecules of chloroethane, this will react with two atoms of sodium in the presence of dry ether to give C4H10. And NaCl, sodium chloride, will be given out as a byproduct. What happens here is the halogen atom of one molecule Suppose this is one molecule of chloroethane and the second molecule C2H5 again. The halogen atom is replaced by the alkyl group from the second molecule. So we get C4H10, and these two chloride atoms will combine with sodium metal to form NaCl. So with sodium metal, these haloalkanes, they give rise to alkanes, and this reaction is called as the Wurtz reaction. Try to remember this reaction because this is a very important reaction of the haloalkanes. Just like the haloalkanes, haloarenes also have three different types of chemical reactions. The first type of chemical reactions of the haloarenes is once again the nucleophilic substitution reactions. So just like in the haloalkanes, in nucleophilic substitution reactions of haloarenes also, the halogen atom is replaced or substituted by a stronger nucleophile. But the very important thing to remember here in this reaction is that haloarenes, they are less reactive towards this nucleophilic substitution reactions as compared to that of the haloalkanes. Now there are two reasons why haloarenes are less reactive in this case. The first reason is because of resonance, and the second reason is because of differences in hybridization. Now, if we see the structure of these haloalkanes, in the haloalkanes, the halogen atom is bonded to a carbon atom of an aliphatic chain. But in haloarenes, halogen atom is directly bonded to an aryl ring. Now, all the halogen atoms, they will have 7 electrons in their valence shells. Now, out of the 7 valence electrons, 1 is shared with a carbon atom of the ring here, and therefore this halogen atom will have 6 electrons in its valence shell. Now, a pair of electrons from here, from the valence shell of the halogen, can come here and form a bond, and this bond becomes a double bond. So when that happens, the halogen will now have only 4 electrons in its valence shell, but a double bond is formed here, and this bond gets broken. The pi electrons will come out here, and this will carry negative charge. So what happens is, this bond gets broken, and the electrons have come out here. These 2 bonds will remain. Now, these electrons again can come in and form a bond here. Therefore, this bond breaks and the electrons come out like this. So we get another structure where the halogen still has a double bond. A bond has been formed here. This bond is broken and the electrons have come out here. This bond still remains. Then this electrons once again comes in and form a double bond here, and therefore this bond breaks and the electrons come out. So another structure is obtained where halogen atom still has a double bond. This bond remains, a new bond has been formed here, and this bond has been broken and the electrons have come out here. Then these electrons come in, attack this to form a double bond. When that happens, this bond breaks and the electrons come out to the halogen atom. So another structure is obtained where now the halogen atom has only a single bond but 6 valence electrons. The bond has been formed here and these 2 bonds remain. So the electron pairs of the halogen atom are in conjugation with pi electrons of the aryl ring, and this leads to these resonating structures. Now the actual structure of the haloalkane will be a contribution from all of these resonating structures, and therefore in the actual structure the CX bond, the carbon to halogen bond, is neither a single bond like this nor a double bond like this. It will be a contribution from all of this. So the CX bond will be a partial double bond, and double bonds, they are stronger than single bonds. Therefore they are more difficult to break and the reaction becomes slower. The second reason is due to hybridization. Now if we just see the carbon atom in this haloalkane, this carbon atom will be sp3 hybridized. But in the haloarenes, the carbon atom, since it has partial double bond character, it will be sp2 hybridized. Now sp2 hybridized carbon atoms, they are more electronegative, and due to the more electronegativity, the carbon atom will attract the bonding electrons from the CX bond more strongly, and because of that the bond becomes shorter, and when it becomes shorter it becomes stronger, and once the bond becomes stronger the reaction becomes slower. Therefore, due to resonance and due to hybridization, the nucleophilic substitution reactions in haloarenes are much lower than that of in haloalkanes. Another important point to remember in this nucleophilic substitution reaction of haloarenes is that when there are some electron withdrawing groups present in the aryl ring, especially at ortho and para positions, the reactions become faster. Let us see an example here. If we have chloropenzene, which is a haloarene, this chloropenzene, if it is heated with sodium hydroxide, then we get phenol. The halogen atom is substituted by the OH group from the base. Now this reaction takes place only if we heat the reaction mixture up to 623 Kelvin and a pressure of around 300 atmosphere is applied. But if this chloropenzene contains an electron withdrawing nitro group at the para position, the same reaction takes place. OH group will replace the halogen atom here. But the thing is, this reaction takes place at a much lower temperature, that is at 443 Kelvin. Similarly, if there are two NO2 groups, one at ortho position and the other at para position, the same reaction will take place. Substitution will take place again. Cl group will be replaced by OH group, but in this case, the reaction takes place at around 368 Kelvin. Now, if we have three nitro groups, one at para position and two at the ortho positions, then the reaction takes place by just warming the reaction mixture. So we see that if there are electron withdrawing groups like nitro group at ortho and para positions, the nucleophilic substitution reaction becomes much easier and faster. But no such effects are observed if the electron withdrawing group is present at meta position. Now the next reaction of these haloarenes is the electrophilic substitution reactions. Now haloarenes, they show all the typical electrophilic substitution reactions as shown by benzene, like the halogenation reaction, nitration, sulfonation reaction, the Friedel-Crafts reaction, and so on. But these electrophilic substitution reactions in the haloarenes, they occur much more slowly and under more drastic conditions than that we see in benzene. So why does this happen? Why are these electrophilic substitution reactions in haloarenes much slower, and why do they occur under more drastic conditions compared to that of benzene? Once again, there are two reasons for this. The first reason is that due to resonance, we have seen the resonating structures of these haloarenes. Due to resonance, this halogen atom directs the incoming electrophile to ortho and para positions. If you see the resonating structures of chlorobenzene, you will find that in 3 of the structures, that is at ortho and para positions, you will find negatively charged electrons. And those are the centers where these electrophiles will attack. So the halogen atom will direct the incoming electrophile to ortho and para positions, whereas in benzene, the substitution can take place at any of these positions easily. The other reason is that due to the presence of this halogen atom, which is highly electronegative and which causes negative inductive effect, the electron density on the benzene ring decreases. That means the halogen atom, due to its negative inductive effect, deactivates the ring. And it is for these two reasons that the electrophilic substitution reactions of haloarenes occur more slowly and under more drastic conditions compared to that of benzene. Let us quickly see one example of these electrophilic substitution reactions. Halogenation. In halogenation reactions, we treat these haloarenes with halogens in the presence of catalysts like iron chloride. Now, as I've mentioned before, the halogen atom on the ring here will direct the incoming electrophile to ortho and para positions. Therefore, we get two different types of products. In one, the substitution has taken place at ortho position, and in the other one, substitution has taken place at para position. So in every electrophilic substitution reaction, you will find that the substitution has taken place at ortho and para positions, and we will get a mixture of these two different types of products, para and ortho isomers. So that is all the time we have for today. We'll continue in the next class.